let's look at this first example. So in this example, we have x prime y prime equal to a times xy plus a vector with scalar say b1, b2. In our case, x prime y prime equal to a times xy plus 0, minus 2, 0, minus 2. And a here is just a coefficient matrix 1, minus 2, 3, minus 4. So this case, first of all, we know that in this case we have say x naught y naught is a critical point, and by doing the variable u equal to x minus x naught, v equal to y minus y naught, you can bring this system to the linear system x prime y prime equal to a times x, and the behavior around the critical point x naught y naught here will be exact same thing as the behavior around the critical point 0, 0 of this homogeneous linear system. So just by changing the variable. So before we work on that, we need to find the critical point x naught y naught, and to find that you just solve for xy so that this one equal to 0 and this one equal to 0. So here I did that, and x minus 2y equals 0, x equal to 2y, and you plug in x equal to y to here. You have 6 times y minus 2y, 4y equal to 2 times y equal to 2, therefore y equal to 1, and then x equal to 2 times 1 equal to 2. So we know critical points of the system they give us is 2, 1, and we have only one critical point. That one is isolated critical point. Now we change the variable to bring that original system to a linear system. So the changing variable we have is u equal to x minus 2 and v equal to y minus 1. Now we just need to write down this system in terms of u and v. We need to compute dx over dt. So u equal to x minus 2, so du over dt is just dx over dt. And if you do derivative here, this one will be 0. Similar for the second equation, dv over dt is just dy over dt minus 0. And now we plug this in. X now equal to u plus 2. X equal to u plus 2 and y equal to v plus 1. Now we have enough data to plug in here to change the variable. Dx over dt is equal to du over dt. X equal to u plus 2. 2 times y equal to v plus 1. dy over dt is dv over dt. So this one I use. 3 times x, so 3 times u plus 2 I use. X equal to u plus 2. Minus 4 times v plus 1 minus 2. So the first equation I have u plus 2 minus 2v minus 2. So 2 minus 2, so we have u minus 2v. For the second equation, 3 times u minus 4 times v plus 6 minus 4 minus 2 plus 6 minus 4 minus 2, which means 3u minus 4v. So you see that we bring the original system to the new one, du dt u minus 2v dv over dt 3u minus 4v. Or if we want to write out in terms of the matrices form, you have u prime v prime equal to a times uv. A in this case 1 minus 2, 3 minus 4 times u and v. Now you look at this one, or this one, exactly this form. So next time you don't need to do all of those changing variable again. If you see this case, the x over t is something linear, everything linear here, and plus minus just some number, some scalar b1, b2, then you know that you can always think about it as a linear system, homogeneous linear system. The matrix here in our case has a determinant of this, and we call this A. This matrix, that calls A. Determinant of A is minus 4 plus 6, so non-zero. So the only critical point we have is 0, 0. Because if you solve this, it will be 0, 0. You find the critical point is the only solution is a trivial solution. U equals 0, V equals 0. The only critical point is 0, 0. What happened near 2, 1 is exactly same as what happened near 0, 0. Now we need to classify the type and the stability of that critical point. That one is 2, 1. That is the exact same type and exact same stability of 0, 0. The type and the stability of the critical point of 2, 1 of the original system. Is the same or are the same as that of 0, 0 of the linear system. U prime v prime equal to a uv, and actually this A is also the Jacobian matrix of this. If you want, if you compute that at the point 0, 0, we know that that matrix A is actually the Jacobian. So now we use the eigenvectors methods. We compute the eigenvalues of A. Matrix A is 1 minus 2, 3 minus 4. Compute determinant of this one. You have lambda minus 1, lambda plus 4 plus 6, lambda square, 3 lambda minus 4 plus 6, so lambda square, 3 lambda plus 2, which gives us lambda plus 1, lambda plus 2. So we have two distinct real eigenvalues, lambda equal to minus 1, lambda equal to minus 2. So distinct eigenvalues, we know that the behavior of that critical point, we have two eigenvalues as a negative correspond to that of two linearly independent eigenvectors. So along that, they both sink into the origin because they are negative. And then the rest just follow the two. So I don't draw the exact picture, but you see that, for example, in this quadrant, it's going to follow one, follow the other one, like that. So it will be a sink. And this one, you see that it is improper nodal sink. Nodal sink. And it is, the type is asymptotically stable. They asked us about the type and the stability. This sink is actually a node. So it is a node, and that node, and that node is asymptotically stable. And therefore, the behavior of the type and the stabilities of the original critical points of the original system minus 2, 1 is also the same thing.